I'm just going to talk you through this PowerPoint on expected outcomes, which is the next thing that we're doing in probability. So expected outcomes is talking about like what you expect to happen or what you think could happen based on the probability of a certain event or a certain outcome. So here we've got a fair coin, which means that both sides of the coin have the same probability of happening, and it's flipped 10 times. Which of these do you think is the most likely outcome? So that it lands on heads all 10 times, that it lands on tails all 10 times, or that it lands on heads 5 times and tails 5 times. Now, hopefully it's obvious that it is the third option that is the most likely, because the probability that it lands on heads is a half, and the probability that it lands on tails is a half. Half of 10 is 5, so the most likely thing to happen is that it lands on each of the different outcomes 5 times each, because the probability of both of them is a half, and a half multiplied by 10 is 5, or half of 10 is 5. Remember that whenever you have a multiply or whenever you see of, it means times and vice versa. Okay, so this time we've got a fair dice. So again, that means all 6 numbers on the dice have the same chance of happening, have equal probability. And it's rolled 3,000 times. How many times would you expect it to land on 3? So if the probability of it landing on a 3 is 1 out of 6, because there is 1 3 on the dice out of 6 possible options, then we have to multiply. Okay, that's the next question, but we'll go through this one first. Then we have to multiply the probability of it landing on a 3, which is 1 over 6, by the number of times we are rolling the dice, which is 3,000. So that's 1 over 6 multiplied by 3,000, which is 500. So we would expect it to land on a 3 500 times. That doesn't mean that it will land on a 3 exactly 500 times. The whole idea of a probability is that it is something that is likely to happen. That's what we expect to happen, but in real life, what we expect to happen doesn't always happen. So we would expect to land it around 500. It's less likely that it actually lands on it 500 times exactly. It's probably going to be somewhere close to that. But that's how we work it out. We take the probability and we multiply it by the number of times you are conducting the experiment. How many times would you expect it to land on a prime number? So they often expect you to have basic number skills in these types of questions. So you need to know how many prime numbers are on a dice to be able to answer this question. Which there's 3, so 2 and 3 and 5 are all prime numbers. They're the only ones that are on the dice. So there's 3 out of 6 numbers altogether, which is a half. And then this time we multiply that probability, so a half multiplied by 3,000, which would be 1,500. Again, that's an expectation. That doesn't mean that is what will happen all the time, but that's what we expect to happen. Right, now we've got a spinner with different colours on. It's spun 400 times. Dexter thinks that the spinner should land on red 160 times. Do you agree? Well, let's have a look. Let's work it out. So the probability that it's landing on red is 2 out of 5. So we would take that probability, because there's 2 red sections out of 5 sections altogether. So the probability is 2 out of 5, and we multiply that by 400, which is 160. So yeah, we agree with Dexter. Dexter has done the correct calculation and he's got the right answer. The spinner should land on red around 160 times, but not necessarily exactly 160 times. So Dexter's right in that that's what we expect to happen, but it's probably not going to land on it 160 times exactly. It will be somewhere close to 160. A coin is biased, okay, so this one, we're not getting an equal probability of it landing on heads and tails. This coin's biased, so the probability that it lands on heads is 0.47. How many times would you expect a coin to land on heads after 125 throws? Again, we do the same thing, except our probability is a decimal now, but that's fine. And we multiply the probability by the number of times you're throwing the coin. Okay, I didn't realise Eva was doing something. Here's Eva's working. So the probability that it lands on heads is 0.47. The expected number is 0.47 times 125, which is 57.85. The coin will land on heads 57.85 times. Can you improve Eva's answer? What she's done is fine. Her working out is perfect. But the issue is obviously with 57.85. How does it land 0.85 times on heads? So we would round it. So we would round that 57.85 up to 58. And again, using the word about or approximately just makes it a more realistic answer. It's not going to land on the heads exactly 58 times, but it's going to be somewhere close based on the probability. Okay, another coin is, again, it's biased, so the probability that it lands on heads is 3 times the probability that it lands on tails. How many times would you expect the coin to land on tails in 1,000 throws? The first thing we need to do here is work out the probability of it landing on tails. They haven't told us exactly, they've just kind of given us, I mean, essentially it's an equation that we need to solve to work out the probability of both. So the probability that it lands on heads is 3 times the probability that it lands on tails. So if we call tails x, then heads would be 3x because it's 3 times the probability that it lands on tails. We know that probabilities always have to add up to make 1. So we know if we add the probability of heads, the 3x, with the probability of tails, which is x, then that's going to give us 1. X add 3x is 4x is equal to 1, and then divide by 4 to get the probability of x, or to get the probability of tails. So x is 1/4. Heads is 3 multiplied by 1/4, which is 3/4. But we're only interested in tails for this question. But that's what heads would be. Heads would be 3/4 and tails would be 1/4. To work out the expected number of tails when we throw that coin 1,000 times, we take our probability, which is 1/4, multiply it by 1,000, which is 250. So we would expect it to land on tails 250 times. Okay. I didn't realise we still had more questions. The table shows the probabilities of getting different coloured sweets from a bag. So we've got blue is 0.1, yellow is 0.2, purple is 0.35, and green is something that we don't know, so we're calling it X. In an experiment, a sweet is taken from the bag and replaced several times. By replacing it, it means it doesn't change the probabilities because you're taking it out and putting it straight back in again. As we move through this topic, we'll have a look at what happens if we take the sweet out and don't replace it. But for now, all that means, the only reason that it's important that we're replacing it is because it means the probabilities stay consistent. We've got 70 green sweets were selected. Estimate the total number of trials of the experiment. To start this off, we need to know the probability of green. So we need to use, again, the fact that all of the probabilities have to add up to 1. So we can add up the ones that we've got, so the 0.1, the 0.2, and the 0.35, and subtract that answer from 1. That will give us the probability of green, which is 0.35 as well. We know that that probability is equal to 70. Okay, so we haven't picked 70 sweets in total, we've picked 70 green sweets. So we have 0.35 is equal to 70. So we know that if we did 0.35 multiplied by the number of trials, so the number of sweets we picked out in total, then it gives us somewhere close to 70. So to work out the number of trials, we could divide 70 by 0.35. And that would give us the number of trials is about 200, okay? We're using approximately, that's what this wiggly equal sign means. It means it's approximately equal to. Again, because this is expected, it's probability, nothing's ever exact. It's always given us an estimate or an approximation. Okay, and that's the end of the slides. I know I've gone through that really quickly. Time was against me today, but use that to go through your Google Slides, please, and make sure you hand everything in at the end of the lesson. Yeah, Okay, thanks, girls.